How would you measure the distance that an angle moves? Maybe for the angle on the right, you might say if you start here on the initial side and move a certain amount, maybe 35 degrees, that's one way to express what's going on here. But there are other ways that we could express angular movement besides just using degrees. Suppose that we start with a circle and we're going to consider the center of the circle. And we're going to draw an angle in here. We'll start with this side. So notice if it goes from the center out to the circle, we call this the radius. So let's say we've measured the radius and we go that exact amount around the circle. And we say, let's find out what the angle is that we just created. So let's call this angle theta. Well, to get this angle theta, there were two things that we're comparing. We compared the distance that we went around. So we went around a distance of r, and we compared that with the radius, which is also r. So if we call that comparison theta, then this is going to be exactly 1. Keep in mind that we were using the radius as a reference, so this is basically what we mean when we say 1 radian. So 1 radian is the angular distance that is traveled by exactly 1 radius length. So since we know that, how do we represent the entire distance traveled around the circle? If we started here and kept going the entire distance around, what do we normally represent that as? We would normally call that the circumference. And the circumference is represented by the formula 2 times pi times the radius. So as opposed to going a length of r, we're actually going, if we go around the whole circle, we're going a whole length of 2 times pi times r, the entire circumference. So what we want to do is we replace r with 2 times pi times r, so we'll think about what the angle measurement would end up being. So if we did that, our new formula would be theta is equal to 2 times pi times r over our radius. Of course, the radius would cancel out or divide out, and we would just be left with 2 pi. So if we went the entire distance around the circle, we can call that 2 pi radians. So 1 full trip around the circle, we know gives us an entire circumference length. So 1 trip around the circle would be 2 pi radians. But what if we only went halfway around? So let's say we started here and we stopped here. In other words, we only went halfway around the circle. What angle would be formed? Well, in this case, since we only went halfway, then we would have only gone pi radians around the circle. What if we went half of that? So if we went half of that, that would put us here. That means we would have gone pi over 2 radians around the circle. And if we continued, then basically if we went from here, remember this is 1/4, 2/4, and here would be 3/4 the way around the circle. If we do 3/4 of our entire circle length, which is 2 pi, then when we simplify it, both of these divide by 2, so that'll be 1. This divides by 2, that'll be 2. Basically, we would have gone 3 pi over 2 radians around the circle if we stopped here. And if we kept going, that will put us back here at 2 pi radians. So from what we know so far, if we started here and went 1/4 the distance around the circle, we would have gone pi over 2 radians. If we went halfway around the circle, we would have gone pi radians. If we went 3/4 of the distance around the circle, then we would have gone 3 pi over 2 radians. And if we went one entire distance around the circle, then we would have gone 2 pi radians. So let's compare that to what we know about degrees. If we went just 1/4 of the way, we would make this angle. What's this angle equal to? Well, we know that this angle is 90 degrees. So from what we know, then pi over 2 is the same as 90 degrees. If we went halfway from here to here, then we would have gone 180 degrees. So from what we know, pi is equivalent to 180 degrees. And we can keep going if we wanted to. So 3 pi over 2 would be 270 degrees, and 2 pi would be one full rotation of the circle. That's 360 degrees. Notice that all of this basically means the same relationship. If we divided both sides here by 2 to get pi by itself, then pi is 180. That's what we already said here. If we multiplied this side here by 2/3 and this side by 2/3, then we end up with pi equals 180 degrees. So however we look at it, one relationship that will always remain constant is the fact that pi and 180 degrees, so pi radians, is the same as 180 degrees. Which brings us to how do we actually do this conversion? So let's say that we have 360 degrees and we need to change it to radians. Well, what we could do is we could say, let's just multiply this by 1. That's not going to change it at all. But we know that, let's say that we divided both sides by 180 degrees. Then we can represent that 1 as pi radians over 180 degrees. Or if we did the division the other way, we start with pi radians equal 180 degrees. And let's say that we divided both sides by pi radians. Then what that means also is that that 1 can also be represented as 180 degrees over pi radians. So if we want to get radians on this side, then what we could try and do, let's put this 360 degrees over 1, and we're going to multiply it by pi radians. Let's write this out actually. So this 360 degrees, I'm going to actually write the word. So we have 360 degrees, and we're going to multiply that by some equivalent of 1. So we're going to multiply it by one of these. So if we multiplied by pi radians over 180 degrees, remember the 360 can be put over 1. So we know we can simplify this. If you ever did unit analysis, you know that these degrees basically are going to divide out, and the 180 and the 360 are both divisible by 180. So this will give us 2 here. Excuse me. This will give us 1 here if we divide it by 180. And this divided by 180 would give us 2. If we multiply it straight across, we'd end up with 2 pi over 1. So from what we just said, our calculation shows us that 360 degrees is the same as 2 pi radians. So to make a long story short, if we want to go from degrees to radians, we're going to multiply by this conversion factor. And if we want to go from radians to degrees, we can multiply by this conversion factor. Or we can just remember that pi radians is the same as 180 degrees. So if we were to do that, we could say there are 2 ways to really work out the following. Suppose we had pi over 2 radians and we wanted to know what it's equal to in terms of degrees. We could say that pi is the same as 180 degrees. So we would have 180 degrees over 2, which gives us 90 degrees. So we can say pi over 2 radians is 92 degrees, 90 degrees. Or we can say that pi over 2, we can multiply by the conversion factor. So we want degrees. So we're going to have degrees up at the top. And we are going to multiply by pi 180 over pi. So the pi's divide out, and when we multiply across, that's going to be 180 over 2, which ends up being 90 degrees. So we have more than one way. Either we can use a conversion factor, or we can just use the fact that pi is the same as 180. Another fact that's important to note is what exactly do we mean when we say the standard position of an angle? So concerning the vocabulary standard position, whenever we draw an angle in the plane, what we want to do is to put the vertex on the origin. Also, we're going to put what's called the initial side. We're going to put that on the x-axis. And we're going to have our terminal side be in any of the 4 quadrants. In this case, our terminal side is in quadrant 2. And if you ever forget about how to number the quadrants, this is quadrant 1, this is quadrant 2, here's quadrant 3, and here's quadrant 4. So our terminal side is in quadrant 2. And if you, again, want to remember how to do this, simply just draw the letter C. So C would start here, 1, 2, 3, 4. So that tells us how to write an angle in standard position and how to identify where the terminal side of that angle is. Here's another angle in standard position. Notice again that the initial side is where it should be. The initial side is on the positive part of the x-axis. We have our vertex at the origin, and our terminal side is in one of the quadrants. Actually, it could also end up being between the quadrants, but in this case, our terminal side is in quadrant 1. So here's a non-example. Notice that our initial side, this is not in standard position because our initial side is not on the x-axis. Also, our vertex is not at the origin, but our terminal side is in one of the quadrants. So what makes this fail as an angle that's not in standard position is the fact that the initial side is in the wrong place. Also, the vertex actually should have been here at the origin. We can also have what are called coterminal angles. So by coterminal, we mean that the terminal sides work together. In other words, you have the same terminal side. So let's say that I wanted to make an angle of 30 degrees. So if I wanted to make 30 degrees, I would say start on the positive part of the x-axis and then move until it reaches 30 degrees. So this is 30 degrees. But let's say that I wanted, as opposed to 30 degrees, let's say that I wanted 390 degrees. So for 390 degrees, I would still start on the positive part of the x-axis. Then I'd basically count until I have 390 degrees. So I'd end up here, 90, 180, 270, 360. But now I need to do another 30 to end up at 390. So in other words, this 390 represents a full rotation of 360 degrees plus 30 degrees, which puts me back in the same spot. So in other words, 30 degrees and 390 degrees are coterminal. They end in exactly the same spot. It works also if I were to go the other direction. So if I count counterclockwise this direction, I'm creating positive angles. So clearly, positive 30 is coterminal, or has the same terminal side as 390 degrees. They end in exactly the same place. But what if I wanted to think about some negative angles? So suppose that I wanted negative 330 degrees. So for negative 330, I'd have to go clockwise to make a negative angle. So this is negative 90 degrees. This is negative 180 degrees. This is negative 270 degrees. But we need to go a little bit further. If I go another 60 degrees, 270 plus another 60 degrees should put me at 330 degrees. So if I go another 60, that puts me back on the same terminal side. So what I know is negative 330 degrees has the same terminal side as a positive 30 degrees. So to make a long story short, if I can add 360 degrees to an angle, or if I can subtract 360 degrees from an angle, then that means the two angles are coterminal. For example, to 30 degrees, if I add 360 to it, it gives me 390 degrees. So this angle and this angle, they're going to be coterminal. Similarly, if I took that same 30 degrees and I subtracted 360, I'd end up with negative 330 degrees. So negative 330 degrees is coterminal with 30 degrees. We also need to know what a reference angle is. And what we mean by a reference angle is that this angle has to have a vertex on the origin. As well, we're going to basically go from the terminal side of that angle to the x-axis, and that's going to create a reference angle. So in this case, 30 degrees is our reference angle. But suppose that we had an angle of 150 degrees. So for 150 degrees, what's the reference angle? Well, we're going to say we need to go from the terminal side to the x-axis, and we want to find the shortest path. So from there, this is the shortest path. So this is our reference angle. In this case, our reference angle is 30 degrees. So 150 degrees has the same reference angle as 30 degrees. So suppose that we did this movement of 330 degrees, and we were asked, what is the reference angle? Remember, we're going to start from the terminal side and go the shortest path to the x-axis, and that's going to be our reference angle. So this is our reference angle, again, 30 degrees. So 330 degrees has a reference angle of 30 degrees. If we had, let's say, a movement of 210 degrees, what would you say the reference angle is? Pause it, think about it, think what you would say about that. Well, we said that the reference angle is that short angle between the terminal side. So remember, this is our terminal side, between the terminal side of the angle and the x-axis. So that's basically this angle here would be our reference angle. We know that from here to here, we would have had gone 180 plus another 30 to make 210. So just this piece here would give us 30 degrees for our reference angle. Let's recap what we just found out. If we had an angle whose terminal side, this is the terminal side that I'm creating, whose terminal side is in quadrant 1, and again, remember the quadrants are 1, 2, 3, 4. So if we have a terminal side in quadrant 1, for example, 30 degrees, then what's the reference angle? So for 30 degrees, the reference angle would just be 30 degrees. So all angles in quadrant 1 have exactly the same reference angle. But if we're in quadrant 2, so let's say that we made this angle whose terminal side is in quadrant 2, and suppose that this angle starting from the initial side to the terminal side has a measurement of 150 degrees, what would the reference angle be? We just said that the reference angle would be the shortest distance, shortest angular distance between the terminal side and the x-axis. So that's the shortest distance, which is 30 degrees. We would not go back the other direction. So this is definitely not the shorter angular distance. So think about how we got there. We know that the full distance from here to here is 180 degrees. But if all we did was go from here to here, we only went 150 degrees. That means that we have another 30 to go. In other words, with our angle in quadrant 2, we said that we took 180 and subtracted our angle to get our reference angle. Similarly, if we have an angle that has a terminal side in quadrant 3, for example, if we have 210 degrees, we would have gone a whole 180 degrees plus a little bit more. So to figure out our reference angle, which in this case is 30 degrees, that's this piece here, we would have said in quadrant 3 that we took our angle, which was 210 degrees, and we subtracted it with 180, and that gave us our reference angle. But if we had an angle in quadrant 4, let's say, for example, that we had 330 degrees, whose terminal side ends in quadrant 4, that the reference angle would be this, because that's the shortest angular distance between the terminal side and the x-axis. We know that this is a distance of 30 degrees. So how did we get that? We said 360 degrees, take away our 330, gives us the angular distance we would need to make it back to the x-axis, so that would be 30 degrees. So for an angle in quadrant 4, we would need to take our angle and subtract it with 360 degrees to end up with our reference angle. So there are a few basic patterns that we can use when we're describing this. So again, quadrant 1, what's our reference angle? So whatever angle we're given is the reference angle. Quadrant 2, we would need to take 180 degrees, subtract it with the angle that we're given, and that's going to give us our reference angle. For quadrant 3, what we just discovered was that we would take our angle that we're given, subtract it with 180, and that would give us our reference angle. And finally, for our fourth quadrant, we found out that we're going to subtract this time with 360 degrees. So whatever angle we have, we're going to take that and subtract it with 360 degrees, and that's going to give us our reference angle.